When you write code, the compiler translates your human-readable loops and variables into an intermediate representation, a sequence of elementary machine steps. But looking at this generated code as a flat, linear list is dangerous. If you want to optimize it by reordering or deleting lines, you face an immediate problem. There is no context. If an optimizer naively shifts instruction 5 to save time, it might break a jump command originating at instruction 50 that was explicitly targeting line 5. To safely manipulate the program, the compiler has to abandon the linear list. It needs to build a spatial, two-dimensional map that models exactly how control flows from one command to the next. This structural abstraction is called the flow graph of basic blocks. Without converting flat text into this geometric map, any attempt to optimize performance wouldn't speed up the software. It would simply break the program's logic. We're going to trace the exact mathematical algorithm compilers use to map this code topography. The methodology we are following is laid out in the definitive text on the subject: compilers, principles, techniques, and tools. Our starting state is raw, sequential 3-address code. The derivation happens in 3 strict phases: partitioning the code into isolated blocks, resolving the state of the variables within them, and finally networking those blocks into a global graph. This mapping process relies on rigid, unyielding mathematical axioms. It requires a complete shift in perspective. The machine discards the human readability of the code in favor of pure geometric logic. This diagram shows a vertical column of 10 generic 3-address code instructions. First, the compiler partitions this list into basic blocks. These are code sequences with impenetrable borders. Execution flow only ever enters at the top instruction and leaves at the bottom, without halting or branching in the middle. To find these borders, the compiler scans the list to identify specific instructions called leaders. These leaders dictate exactly where to slice the code. Rule 1. The very first instruction in the intermediate code sequence is by default a leader. Rule 2. Any instruction that acts as the target destination of a conditional or unconditional jump is a leader. Rule 3. Any instruction located immediately following a jump command is also a leader. Once all leaders are identified, the compiler builds the blocks. A block consists of its leader and all subsequent instructions, right up to the start of the next leader. The code is now physically separated into discrete, unlinked logical units. Inside these tightly partitioned borders, execution is entirely deterministic. The compiler has created a safe sandbox where it can perform deep local optimizations without worrying about outside interference. Inside this sandbox, the compiler has to figure out exactly how to allocate the CPU's limited physical registers. To do this, it tracks a property called liveness. A variable is live if its value will be used again. The exact moment it is never used again, its register can be recycled for something else. This side-by-side diagram shows our single basic block of code next to a blank symbol table tracking liveness and next use. Determining this data requires a counterintuitive approach. The compiler must scan the block of instructions in reverse. This is called a backward pass. The process begins at the bottommost statement of the block, for example, x equals y plus z. Step 1. The compiler looks at the symbol table and attaches the current known liveness data to this specific instruction. Step 2. It evaluates the computed result, variable x, and marks it as not live. Because we are moving temporally backwards up the block, any instruction we scan next happened before this value was created. Therefore, earlier instructions cannot possibly use this version of x. Step 3. The operands used to calculate x, variables y and z, are marked as live, and their next use location is updated to point directly at this current statement. The scan line moves up to an instruction like x equals x plus 1, highlighting the shared variable name. The order of these steps is rigid. You cannot swap steps 2 and 3 because a variable might be used as both an operand and a result in the exact same line. By traversing the code in reverse, the compiler perfectly predicts the future resource demands of the program without executing a single line. Looking at this zoomed-out mapping of multiple scattered blocks, we can see how the compiler transitions from the microenvironment of a single block to the macroenvironment of global flow. It evaluates jump commands and fall-throughs to draw directed edges between the blocks. A complete graph requires definitive start and end points to anchor the analysis. The compiler generates two theoretical nodes, an entry node linking to the first block, and an exit node connected to any block that could terminate the program. This closed, interconnected network is formally recognized as the flow graph. The primary reason the compiler builds this specific geometry is to locate the loops. Software spends the vast majority of its time cycling through repetitive instructions, making loops the most critical targets for optimization. In graph theory, a loop requires two specific features. First is a single entry node called the header, which dominates all other nodes in the sequence. Every path into the loop must bottleneck through this specific header. The second requirement is a backedge, a directed path that retreats from a block lower in the graph straight back up into the header, completing the circuit. To the compiler, human-readable constructs like while and for loops do not exist. A loop is exclusively defined by this geometry of backedges. We started with a contextless, linear text file. We finish with a strict topological map. The basic blocks secure highly optimized local register allocation, while the flow graph secures a global understanding of execution paths. Operating on this topology completely removes the risk of inadvertently breaking the program's logic during optimization. It also provides the foundation for building even more advanced structural models, like directed acyclic graphs. Ultimately, compilers act as the master architects of execution space, rebuilding human program logic into these vast, complex structural models. By mathematically modeling the structure of the code, it guarantees processing speeds that raw line-by-line translation could never achieve. And achieving that extreme efficiency often requires looking at the problem backward. True optimization relies on destroying the original text and rebuilding the program as a permanent, multidimensional mathematical landscape.